Hey guys, so if you're getting this video, that means that you are absent for the 4.1 wave motion lab. So with this lab, our main objective is we're going to be able to calculate wave speed and frequency. And then what we want to know is does changing the frequency of a wave affect how fast the wave moves, or changes the wave speed? Okay, so uh, in order to do this lab, what we did is we had big springs and we had them out in the hall and we were moving them back and forth. We made different wave patterns or different frequencies of waves. And then we timed how long it took to have 10 complete cycles. And I'll kind of show you that down below. And then we were able to calculate the wave period, the wave frequency, and then ultimately the wave speed using the equation that we learned about. So I'm going to kind of walk you through that. So just remember, as we're doing this lab, do it in your notebook just like we normally would. So you're going to start off with the title of the lab number over by your name, and then our purpose statement, right? So you can see with the purpose on this, again, yeah, we want to be able to describe one full cycle or one wavelength, calculate the frequency and speed of a wave, identify the parts of a wave, and then explain the relationship between waves and energy. Okay. So once you got that written, we can go ahead and jump down to our data table. Okay, so now on this first part, we are going to do what's called a pulse wave. And if you remember from the previous class, if you were here, pulse wave is where we kind of pull the spring, let it go, and it sends a wave down to our partner and comes right back. And we're going to time how long that took. Okay, so for this, as far as your data goes, our partner was 5 meters apart. So when we released the wave, it went down 5 meters and came back 5 meters. So that gave us a total distance of 10 meters. Okay. Now, when we timed this, on average, it took about 0.9 seconds for that wave to get down to our partner and back. Okay, so with this, use those numbers to calculate your wave speed. And so in order to do that, it kind of walks you through the directions. And they suck your soul out. They do. They're terrible. See ya. That was Mr. Daniels. He was telling me about how bad you guys are. Anyway, so it tells you how to do the analysis portion right here, right? So to calculate speed, we're just going to do the distance, which was our 10 meters, divided by our time, which is 0.9. And then we're going to fill that back in on our wave speed, okay? So if you want to pause the video and go ahead and do that, it should just take just a second. Now, part two, what we're doing here is we're going to keep people 5 meters apart, right? So we're going to maintain that same distance. But we can see here, we only have one crest. Okay, so we don't have a full wave. We only have half of a wave. That's going to be important for when we look at wavelength. For this wave, you can see we have a crest and a trough. So we have one full cycle. So we have one wavelength that is 5 meters. And then here, you can see we have, okay, we got a crest, trough, there's one wave, and there's another half. Okay. So when we did this, right? So if we think, okay, we got half of a wave that's 5 meters long, that means a full wave is going to be 10 meters long. Okay, here, very simple. We got one full wave in a distance of 5 meters. So our wavelength is 5 meters. Finally, we got 1.5 waves in a distance of 5 meters. So if we do 5 divided by 1.5, should get 3.33 meters. Okay, so those are our wavelengths, right, for each of these waves. So if we kind of look at this, it kind of makes sense, right? So this is half a wave. The full wave is going to continue out, right, and be about that long. This wave is about half that distance, right? So it's half the 10 meters. This one we have right to about here, so it's kind of like 2/3, right? So 2/3 of that wave. So that's how we got our wavelength. So when we did this, we went through and we timed how long it took to make 10 full complete cycles. So we found with the 10 meter wave, it took about 12 seconds. So we can go and fill that into our data table. For the wave that was 5 meters long, it took about 6.25 seconds. Okay, and then finally, the 3.3 meter wave, or the shortest wave, it only took 4.01 seconds. Okay. Now it's time to do our calculation. So what we need to find is period, frequency, and speed. So frequency we can think of, right, how often something happens. So how often the wave happened in 1 second. So we're going to do waves per second. Period is just the exact opposite. So when we look down at our equations here, there we go on the analysis part, right? Make sure we show our work. We got our wavelength. Then to calculate period, we're going to take our time divided by the number of cycles. Now, this is where everyone gets tripped up. So let's go look back at our data table. So our time is here. That part's easy. So for period, we want to do time, so 12 seconds, divided by the number of cycles, right? So we did 10 cycles for each of these. So we're going to do 12 divided by 10. That's going to give us our period. 6.25 divided by 10. And then 4.01 divided by 10. Okay. Now, if you would have been here, we would have seen the people as they were moving that spring back and forth. On the first one, it's kind of big and slow, right? And then as they went to the next one, it got a little faster. And then finally, the third one was even faster. So the period is basically, we can think of how long does it take for one wave to happen, right? So we can kind of imagine then this one, it makes sense that this number should be the biggest, right? Because it takes the longest for that one big wave to happen. Then as the waves get shorter and shorter, that period, or how long it takes for that wave to happen, gets smaller and smaller. So we should see these numbers start to decrease. Okay, so we're just simply taking our time divided by the number of cycles, or 10 cycles. Okay. Now, frequency. Let's go back to our equation list. So we can see frequency is just the opposite then. So we take our number of cycles, which we know is 10, and we're going to divide it by how long it took to do that, because we want to know waves, number of waves per second. So if we do that here, we know we did 10 waves divided by our 12 seconds. Okay, so we should be able to calculate our frequencies pretty easy. Same thing here. We're going to go number of waves, 10, divided by our 6.25 seconds. And then finally, 10 waves divided by 4.01 seconds. That should give you your frequency. So take a second, go ahead and get those calculations in. And then we're going to talk about wave speed. Okay. Now, I'm going to move myself up here. So wave speed, if you remember, to calculate wave speed, let's look at our equations again on the analysis. We are going to use the equation. We're going to use frequency, the frequency we just calculated, and we're going to multiply that by our wavelength. Okay, so if we just go back to our data table, this is really simple now. So we just found, we just found our frequency, and we just need to multiply that by our wavelength. Okay, so hopefully here you got a frequency of about 0.83, right? 0.83 hertz. And we're going to multiply that by our wavelength of 10, so we should get a speed of about 8.3 meters per second. Okay, so we're going to do the same thing here, right? So we're going to take our frequency that we got here, and we're going to multiply it by the wavelength. Okay, and then finally, same thing, frequency here multiplied by our wavelength. Okay, and that's going to give us our speed. Okay, and last, part 3. So when we went up and did this, we're going to use this wave, right? So we're going to be comparing this to the same wave right here, right? Our middle one. But we just did this on the carpet instead. Okay, so we did the exact same thing. We did 10 wave cycles and we timed how long it took. This time though, instead of 6.25 seconds, it took 8 seconds. Okay, so what I want you to think about is, what are we changing, right? The spring is sliding on the smooth tile, or it's sliding on the carpet. Which one is harder to move through? Okay, what did that do to our wavelength and our frequency? Okay, oh, excuse me. And so now when we look at our synthesis section, what's the relationship between frequency, wavelength, and wave speed? Well, that's our equation, right? So we can use the frequency of a wave, how often it occurs, and the length of the wave to determine wave speed, okay? But what we should notice here is there should be a very clear outcome that if we change our frequency, does that change our wave speed? Okay, so by changing this, did this change? So hopefully it's very, very clear. Now, when we change the medium, going from tile to carpet, did that change our wave speed? That should also be very clear, okay? Email me if you guys have any questions. All right, bye.